2016, no way back. This is to help you to find the results on the datasheet from the information on it. So the first thing we're being asked to do is to show that g, the acceleration due to gravity at the Earth's surface, is 9.81 meters per second squared. You will find this at the bottom of page 2 of the datasheet. But what we need to do is to find the information that's needed from above this. So if I just change the colouring slightly here, the key information. Firstly, Newton's universal law of gravitation, F equals G, capital M, small m over r squared. Now G is a constant and its value is 6.67 times 10 to the minus 11. Capital M is normally the mass of a larger object, so in this case it's going to be the mass of the Earth. Little m is going to be the mass of a person who's standing on the surface of the Earth. And r squared is the distance between the two, which in this case is going to be the radius, well, r is going to be the radius of the Earth, because that's the distance between the center of the Earth and somebody standing on the surface. And we can do a slight change to Newton's universal law to show that it's referring to the Earth by having me referring to the mass of the Earth and re as the radius of the Earth. And we're going to show that you get 9.81 as the acceleration that's being provided. So, firstly, for someone of mass m on the Earth, F equals gmm over r squared is going to become gme little m over re squared. So it's like this, but with the m still there, because we're looking at the force at the moment. Now, if we slot in the numbers, you'll see that where we've got g, I'm putting 6.67 times 10 to minus 11. Where I've got cap me, I'm putting the mass of the Earth, 5.98 times 10 to 24. Little m is the mass of a person, we don't know that, so that stays as little m. And then I want r squared, or re squared, that's the radius of the Earth, 6.378 times 10 to the 6, and it's squared. Now, we could type all this straight into the calculator and see what we got, but just to get a feel for it, we can actually do some calculations with the indices first. And so, if you look at the top here, you'll see 10 to the minus 11, and we're multiplying by 10 to the 24. Now, using the rules of indices, you would add your minus 11 to your 24, and you'll get 10 to the 13. Minus 11, add 24, 13. Also, down here, where we're squaring 6.378 times 10 to the 6, you will square the 6.378, and when you square the 10 to the 6, that's multiplying it by itself, and so 10 to the 6 times 10 to the 6, adding the indices, becomes 10 to the 12. But we can go further. We can cancel these, because when you're dividing, you subtract the indices. And if I subtract the 12 from the 13, I get 10 to the power of 1, which is 10. So this just becomes 6.67 times 5.98 times 10 to the power of 1, 10, divided by 6.378 squared. If we go on to our calculator, we can type that lot in and see what it is all going to become. So I'm going to get 6.67 multiplied by 5.98 multiplied by 10, and then I'm going to divide by 6.378 squared, and it becomes 9.805, so on, 9.805 m. Now notice I've left the m there, that's the mass of the person, and so that's still there at each stage. And this is approximately 9.805, 9.81 m. Now Newton's second law is that force is mass times acceleration. So in this case, if a force is going to be 9.81 m, that's the mass times the acceleration. And so that's the mass part, the acceleration part is the 9.81. So acceleration is 9.81, and it's the acceleration due to gravity on the Earth, which we call little g. So little g is 9.81. Let's go on to the next bit. Show that the acceleration due to gravity at the Moon's surface is approximately 1/6 of the acceleration due to gravity at the Earth's surface. So again, let's look at the information. This is at the bottom of page 3, and you'll see we're talking about the gravity on the Moon's surface is approximately 1/6 that on the Earth's surface. So again, is there any other information above that which is important? If I take this and then show them again, I told the mass of the Moon, we're not told actually what it is, but it is 0.0123 times the mass of the Earth. So it's a lot smaller because it's 0.01. It's about 1% of the mass of the Earth, a little more than 1% of it. But its diameter is 0.273 times the diameter of the Earth, so about 0.27-ish, about a quarter of the diameter of the Earth. So for someone of mass m on the Earth, the gravitational force is gmem over re squared, but on the Moon, notice the force now, Fm, instead of having mass of the Earth, it's become mass of the Moon, suffix m. And instead of the radius of the Earth, I've got the radius of the Moon. Little m stayed the same because I'm assuming the person on the Earth is the same mass as the person who's on the Moon. So, what information can we use here? We're told the mass of the Moon is 0.0123 times the mass of the Earth. So it's 0.0123 times the mass of the Earth. The diameter on the Moon is 0.273 times the diameter of the Earth. Now in both cases, the diameter is twice the radius. The radius is half the diameter. So if I want the radius of the Moon, that's going to be half the diameter of the Moon, and the radius of the Earth is half the diameter of the Earth, and so it's still going to stay in the same proportion. It's still going to be 0.273 times it. So just the same as the diameter of the Moon is 0.273 times the diameter of the Earth, the radius of the Moon is going to be 0.273 times the radius of the Earth, because what we're doing is we're halving both amounts. Now, let's go to what we're told about the Moon. But the force on the Moon is G times the mass of the Moon times the mass of a person over radius of the Moon squared. And let's replace this information with information about the Earth. So where I've got mm, I'm going to put 0.0123 mass of the Earth. And where I've got rm, I'm going to put 0.273 radius of the Earth. And I'm squaring that, so I want to square this one. Now, let's actually compare this with what the situation was on the Earth. But first of all, I'm just going to rearrange it slightly. So instead of having g times 0.0123 mem, I'm going to bring the number to the front. So I get 0.0123 g m mass of the Earth times little m. And here I'm going to square each bit, so I get 0.273 squared radius of the Earth squared. So all I've done here is a bit of rearrangement, and I've squared all of that by squaring 0.273 and the radius of the Earth. Now let's have a look at this. You'll see that you've got your GMEMRV squared there, and we're multiplying it by 0.0123 over 0.273 squared. Now this is the force that's exerted by the Earth. So that's a gravitational force exerted by the Earth for somebody on the surface of the Earth. So it's exactly the same. But on the Moon, it's going to be that times as much. So it's going to, the force on the Moon is this times the force on the Earth. Now let's see what that comes to as a fraction, or let's see first of all what it comes to as a decimal. So if I type in to my calculator 0.0123 and I divide it by 0.273 squared, it comes to 0.165. And so we're saying that the force exerted by the moon is about 0.165 times the force the force that the Earth would have applied to somebody on the Earth. So it's about 0.165 times as much. But we want 1/6. So let's compare 0.165 with 1/6. Well, 1/6, 1 divided by 6 is 0.16 recurving, so it's very, very near to the 0.165. So it's very similar to 1/6 times the force on the Earth. So this is saying the acceleration due to gravity on the moon is about 1/6 of g, because if the force is the same and the mass of a person is going to be the same in each case, because we're assuming the mass of the person on the Earth's got a spacesuit on, just the same as the one on the moon. And so the acceleration due to gravity is going to be 1/6 as much. Let's look at the next one. If the distance between the Earth and the moon is d, and the balance point between the Earth and the moon occurs a distance fd from the Earth, we need to show 1 over f squared is equal to 0.0123 over 1 minus f squared. Well, first of all, let's have a look. This is all on page 4. Let's have a look at what it's actually saying about it before we try the question. So the balance point is where the forces are equal. So you imagine you've got a spaceship that's moving from the Earth to the moon, and it gets to a position where it's a lot nearer to the moon, but the force that the Earth is applying on the spaceship is equal and opposite to the force the moon is applying. We're assuming that this occurs a distance x from the Earth, and so if the distance between the Earth and the moon is d, then that means if this is x and that's d, this little part is d minus x. So for gravitational attraction, if we're looking at from the Earth is g m e m over x squared, because it's g, mass of the Earth, mass of the spaceship this time is little m, that's the object instead of the person, and instead of having radius of the Earth for somebody standing on the Earth, now it's the distance of a spaceship from the centre of the Earth, and that is x, so it's going to be x squared. Then what you're going to get for your next one, oh, that should have moved away. Why is it not doing so? Let's get rid of it. It just doesn't want to go, so I'll cut. It won't move at all, will it? Well, the mass, if what I've got here is the force exerted by the moon, is g times 0.0123 m over d minus x all squared, because the mass of the moon is 0.0123 times the mass of the Earth, and the distance away from the centre of the moon is d minus x rather than x. Oh, this one works okay. And if we're told that the two forces are equal to each other, the force exerted by the moon and the force exerted by the Earth, then you can say that this is the same as that, they're equal to each other. And then the final thing that they're saying on the data sheet is they're saying the distance could be expressed, instead of saying it as x, we can have x as a fraction of d, and so we're labeling it as f times d. Now that means you replace the x by fd there and this x by fd here. And so we've got these are equal. It then says that this can be simplified to this, and that's the task we've got to do. So we take this equation and we try and simplify it to the next equation. So let's see how we do it. So we're trying to get that equation there, and we're starting with this equation here to simplify it to that. Well, the first thing to do is if we can factorize this bit here. So if we take d minus fd, do you see that d is a common factor? So you can remove the d and write it as d times 1 minus f. d times 1 is d, d times f is fd. So we factorize like that. Now that means that if you've got d minus fd all squared, then that is going to be this squared. So it's going to be d squared times 1 minus f all squared. Now let's look at what we're told. We know that this is the same as that. But what I'm going to do is, where I've got d minus fd squared, I'm going to write that in. Where I've got fd all squared, I'm going to square both bits, get f squared d squared. So I get here f squared d squared. Here, instead of d minus fd squared, I can put d squared 1 minus f all squared. Now let's cancel as many terms as we can on each side. So I can cancel the g. That means I'm dividing both sides by g. I can also divide both sides by me, because you see me is on both sides. So that can go. I can also divide both sides, I can move it across, by m. So let's get rid of a little m. And I can finally divide both sides by d squared. So if I do that, let's see what's left. Well, over here, I've got, when you cancel everything down, you're left with just the number 1. So I've got 1 over f squared here. And over here, I've got, well, that was just a times sign. So I'm left with 0.0123 over 1 minus f all squared. So basically, I've actually cancelled it all down. Okay, and got what I want. Right, the last bit we're going to look at in this video is to show that the balance point between the Earth and the Moon is approximately 90% of the distance from the Earth to the Moon. So we already have got this information. You're told that it can be simplified to that, and you're looking for 90%. At the bottom of page 4, you'll see that it's saying about 90% of the distance from the Moon. Let's see again if there are any important bits of information above it. And we've got, this was what we've just shown on the previous page, and we're told that leads to this quadratic, so we need to get from here to here and then to the 90%. So this is what we start with. 1 over f squared is 0.0123 over 1 minus f squared. I don't actually need those brackets there. Okay, first thing, cross multiply. And what we get is 1 times 1 minus f squared is 0.0123 times f squared. 1 times that is 0.0123 times f squared. Next stage, expand this for 1 minus f squared. Well, 1 minus f squared, anything squared, it's times itself. So it's 1 minus f times 1 minus f. So it's 1 times 1, 1 times minus f times 1, and minus f times minus f. 1 times 1, 1 times minus f times 1, minus f times minus f, and minus times a minus, plus f squared. I can gather those together. The minus f and the minus f becomes minus 2f. So I've got 1 minus 2f plus f squared. And then I want to get the f squared bits first. So I'm just rearranging it. And so I'm just writing instead as f squared minus the 2f plus the 1. Now that is the same as 1 minus f all squared. So I can put that as equal to 0.0123 f squared. So I've just replaced that part there by that to get this equation here. Now, it's a quadratic equation, so we want it equals 0 like this. So all we do is we subtract the 0.0123 f squared from both sides. So you're left with f squared minus the 0.123 f squared minus the 2f plus 1 is 0. If I do that subtraction, it comes to 0.9877 f squared. If I do, all I need to do is on my calculator do 1 minus 0.0123, and you'll see it's coming to 0.9877 f squared. So there's our quadratic equation. Well, we know how to solve a quadratic. All we need to do is to go mode 5, the third one for quadratic. The f squareds are 0.9877 equals, and then the f1, that's minus 2, and then the last one is 1 equals, and we'll get two solutions. The first solution, okay, I just lost it, was, let's put it up there again, 1.125, about 1.125. Then our second solution, 0.09002, about 0.0, sorry, I said that wrong, it's 0.9002, 0.9002. So what we've got is those two solutions. Now notice F is showing you, the F is the fraction of the distance from the Earth to the balance point, the fraction of this total distance. Well, if F is more than 1, it means the spaceship is over here. It's actually gone past the moon. It's missed it and having to come back. So it's a balance point over here. You do get a balance point over on this side, where the moon is applying a small force and the Earth is applying a bigger force, and it's obviously a lot nearer to the moon than the Earth, so that does happen, but we want the balance point on this side. So what we need to do is to say that if it is, oh, all of those are just click on them again, okay, and so what we get is that's past the moon, so we want the F as 0.9002, and that multiplied by by 100 to turn it to a percentage, and you're going to get is about 90%. So it's about 90% of the distance away, and so basically it's saying that this balance point is about 90% of the total distance from the Earth. Okay, good luck in your exam, and I'll do another video for the rest of the data sheet.